So our results that we found in the first time around, we found that and what we're going to do is what we found out is our velocity in the end was 7.75 meters per second. But more importantly, if we look here, we've got our energy was 600 joules. That was the work done by gravity. When we went up the ramp, when we fell down the ramp, sliding down the ramp with no friction, we found the same result. We found 600 joules of energy that was done in the end with our network, and we found that the velocity at the end turned out to be the same. And finally, in the third case, we found that 600 joules showed up again, but we found that friction took away 160 joules as well, which ended up slowing us down, which we'd expect it to slow down. But this result over here was a little bit less expected. So the question is, will work done by friction always be negative? Is the first question I asked down here. And the answer is yes, because as we see up here, this -1 is because friction is in the exact opposite direction as our direction of displacement. That's always true. If we drag something along a ramp or along the floor or along a curved surface, don't care what the surface is, if you draw a tangent to the surface, our friction will be directly opposed to the motion at that point. We'll always get a -1 that we have for a cosine of 180 degrees because it works in the opposite direction. Secondly, I asked, we noticed that the kinetic energy and speed at the bottom of the ground regardless of the path. So it didn't seem to bother the box that we went down 5 meters versus 3 meters. They still went up the same speed. Question is why? I'm going to hold off answering that because we've got another homework coming up which will help develop that idea. Now, on the next page, I'll actually go through the answer to part 3. And for part 4, I asked, why is box C slower in the end? Where's the missing energy? Well, the missing energy, was taken away by friction. And the question is, at friction, what does it do? You're losing it to heat. So you're actually using that frictional energy and converting it into thermal energy on the ramp and on the box. So for question number 3, let's take a look at it. Here's a big picture of it. Which would be harder for you to do? To push block A up into the position that it originally started, which would be here, or to push B back up to its starting position, which would be here. All right. And by harder, I asked you to calculate the minimum force required. Well, it's easy to do for box A. If we're going to lift it up at a very slow rate of speed, nice and easy, let's assume it's constant velocity. We'll have force due to gravity acting on the box. So we had a 200 Newton force acting downward. And our lifting force, to lift it up at a nice constant pace, is going to be also at 200 newtons. So that's our minimum force required to lift the box up back to its original position. All right, now let's take a look at the other box. What's the minimum force required to lift this box up? Well, in this box, we're going to have to do a little bit of work here. Remember, when we're pushing it up, we do have gravity to contend with. And we need to break this force down, because we need to, if gravity is trying to pull us down, we need to oppose that force. So I'm just going to bring back our gravity components from before. And as you recall, with this 3, 4, 5 triangle, if this is 200 on this side, we've got the same 3, 4, 5 relationship. And so we're going to have 4/5 of the value over here on the y value. That's giving us our normal force, which is 160 newtons of normal force. And down the ramp, we have, this is a 3, 4, 5 triangle once again. So we've got 3/5 of the force acting down the ramp. And that's the force of gravity acting down the ramp that we've got to overcome. It's 3/5 of 200, which equals 120 newtons. So in order to push this back up, I've got gravity acting down the ramp of 120 newtons. So I'm going to have to push up with 120 newtons to move up at a constant rate of speed. All right. So the answer to part 1 is that certainly it's going to be much easier to push it up the ramp than it is to lift it up the ramp. All right. Second question, which method would require more work? Well, let's look at box A. The work done by you lifting A would be the force you're going to use to lift A times the distance. And the force to lift A is 200 newtons. And our distance is 3 meters. All right, and that's going to take 600 joules of energy. Now, the question is positive or negative? What's the angle between our lifting vector and gravity? It's 180 degrees, so we've got a -1. We're going to multiply, so I get negative 600 joules. All right, so it's going to take negative 600 joules of work for us to let me back up here. This is my lifting force. This is the work that I'm doing. So I'm taking my lifting force and this displacement, they're in the same direction, so we're going to have a positive. I'll have to put in positive 600 joules to lift. All right, so that's for us to lift it straight up. Let's do the same calculation for B. So work for you on B. Well, I'm going to have to use, my force is 120 newtons, and this is the force I'm actually pushing with, and my displacement's in the same direction, so this will be positive as well, and my distance is going to be 5 meters. All right, well, 5 times 12 is 60, so we've got plus 600 newtons. So to move box B up, it takes a lot less effort in terms of the force, but the work you end up doing is the exact same. So we've actually seen a similar situation in class, and this is still, I'll leave this open for bonus. If somebody can tell me what that other similar situation is that we saw, then that'll be worth 2 bonus points. The first person to post something online or email me something can claim those points. All right, now let's take a look at this other set of scenarios here. All right, now we know that in this case the velocity final was 7.75 meters per second, and our work was 600 joules to do this. And when we went down this way, we found out the V final was 7.75 meters per second, and we knew that the energy that it took to do this was 600 joules. All right, and the other thing we knew was the time. We know from our time calculations that this time for A to drop is smaller than the time for B to drop. All right, and I think there's some logic behind our timing, because if we end up at the same speed at both situations, we start at 0, end up 7.75, but we get a longer path on this situation. It just makes sense that if we have a longer path, we're going to be accelerating over a greater distance. If we have a constant acceleration, it's going to take longer time to get up to that speed. So I think there's some logic you can apply to this. And so question number 1 is, which box will be the fastest or slowest as it reaches the ground? So which one will be the fastest as it reaches the ground? Well, in this case, we know we have a tie for A and B, and you're supposed to rank this. So we know that A equals B. What about situations C, D, E, and F? Well, it turns out if you did the work on this, here's the idea here. If we use work kinetic energy theorem to do this, we need to take the force acting on it, and we've got to multiply it by the displacement vector. And it turns out if you look at the displacement vector, here's our final position, here's our initial position. So our displacement vector is right here for this one. It's right here for this one, and it's right here for this one. So that's our displacement vector. And if we take the dot product of our force acting on it, which is gravity, times our displacement vector, there's no difference between this situation, in situation D, it's the same. We've got our same force with the same displacement. Same force, same displacement, and so all these are going to have the same exact velocity when they hit the ground. So for C, D, and E, all right, we can see it's an identical situation. For C, D, and E, should all have the same velocity at the bottom. Just looking at our new dot product idea of what force dotted through different distance displacement means. Remember, displacement is a vector. We're not looking at the distance it travels. Certainly, it looks like E has the longest distance out of these three, but we don't care about distance. We care about the displacement from the starting point to the ending point. What about this last situation? Now we have a displacement that's way down here. In fact, it's the square root of 220 squared plus 3 squared meters is our displacement. Well, if you go back to the last page and look at the math we did, you're going to find out that if we use theta here, we're going to get some cancellation that happens, and it's going to give us, we're still going to have 600 joules of energy used, and it turns out we still have plus 7.75 meters per second. Try the math yourself and you'll see it works. Okay, second question. This relates to time. Which gets to the ground first? Well, they all land with the same speed, but I think this would be the time where you'd want to think about the path, and if you think about acceleration. The question is, if you look at C, D, and E especially, which one of these, compare C versus D. The block as it initially moves from here to here is going to be moving slowly because we've got a very slow ramp here that it's going to go on. Block D, on the other hand, is going to shoot straight down. It's going to gain a really fast velocity really quick, and then the rest of the time it's going to coast along at that high velocity. So if you look at the velocity over time for D, this one shoots really quickly, and then it has a high velocity the rest of the way. This one slowly builds up its velocity, then speeds up at the end. And so between the two, D should be a shorter time than C, should I say. All right. So certainly we can see a relationship there. F is similar to C in that we have a much shallower ramp. We're going to accelerate more slowly down the ramp because the portion of gravity that's in the direction of the ramp, if you break down the vector, is going to be tiny. So it's going to be a tiny acceleration. So you'll slowly build up your speed to 7.75 meters per second, but it's going to take a lot of time. So my guess would be, and you can calculate these, is that F would be probably the longest out of all these. All right. So I would say the time for F is the slowest. Of course, the fastest, I'm going to stick with A because it's going to be accelerating the quickest due to gravity, so we will reach up to the speed quickest. So I would say the time A is less than. I'm going to say time D is probably the next. Then I would say that it looks like time B would be next, followed by time C, and then by time E, then F. And there's some question about exactly where that would fall, but I'm pretty sure that would be as we say. Actually, and E should be faster than C, I would say. So we should probably swap these two. E and C should be swapped. Which has the largest normal force? Well, which one has the smallest normal force? A doesn't even have a normal force, so force normal for A is 0, and that's going to be less than the next one. If we look at this, which one has the highest normal force? Well, the highest normal force is when you're sitting on the surface and equal to gravity, and this one's the closest to sitting on the surface, so that should be the largest. So the normal force of C should be the largest of all these. And then, as you change your angle, your normal force actually gets further and further away from what the gravitational force is. And so it's dependent on your angle. The more horizontal you are, this is the steepest angle, so that's going to be nearly the same as our gravitational drop straight down. You're almost free falling. And so the force normal for D is going to be close to the force normal for A, which is 0. And you can rank order these things in a similar sense based on the angles for each one of these. The steeper the angle, the closer you are to free fall, and the less of a normal force you'll have. The flatter it is, the closer you are to just gravitation pushing straight back up on you, and that'll be larger. Does normal force ever contribute to work? We discussed that in class. You should know the answer to that. Does mass matter? Well, the only way to tell if mass, well, one way to tell if mass matters, well, you could run an experiment. Take your ramp, load it up with maybe a matchbox car. You could do this in class. Take a matchbox car, roll it down with 100 grams on it, and then take a same matchbox car, same ramp, roll it down with 200 grams on it, and see if they match. That's one way you could do it experimentally. You could do it theoretically just by solving these equations with a general solution without plugging any numbers in, but only variables, and you could see if mass cancels in all the relationships. And if you like, go through, I would take the middle problem right here, and instead of putting numbers in here, if you plugged in relationships, and you'd see whether or not mass canceled, and that would give you a good idea, in this case at least, if mass cancels. And you could also try it out for the frictional one to see if mass matters in that one. If we change the mass, would we still end up at the ground with the same speed? Try it out and find out. If you do try that out and come up with general solutions for both of those and get the right result, I'll give you bonus points. For lecture homework 5, we started this in class. And so we already noted on the previous problems that if we look at the free body diagram for the box, we've got gravity acting downward. All right. When we're lifting this box up, we're going to do a lifting force, and we're going to lift this nice and gently, so a nice constant speed. So that also will act with 200 newtons. And I'm going to focus on figuring out the work only due to gravity here, because we already know that the work that you're going to do and or friction does depend on path. We've already established that relationship. I only care about gravity right now, so let's just focus on that. So the question is, how much work is done by gravity? Well, in these segments, these horizontal segments, how much is done by gravity? Well, these are our displacement vectors, these arrows that I have drawn everywhere. These are displacement vectors. So our displacement vectors are perpendicular to our gravity vectors, so our work done by gravity for all these vectors is 0. These are perpendicular. So these are all zeros for the work done by gravity. So we're going to focus on our vertical vectors. And for each of these vertical vectors, let's take a look at this one. Well, our work done by gravity is the force of gravity times the displacement. And if we turn this into this dot product into its equivalent, in these cases, gravity's down, or displacement's up, so we get -1 for that. So we get 200 newtons times 1 meter times -1 equals -200 joules. And all 4 of these pieces are the same, so I have -200 joules of work done by gravity there. And each one of these is -200 joules. All right. So the total of the work done by gravity, I've done 5 steps at -200 joules each, equals a -1,000 joules. All right. Let's look at a different path. So for the next path, same idea. We're only going to worry about the work due to gravity. And we've got no work here, 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 no work here. And so all we have to worry about is calculating the work here, 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 any vertical component. Same sense over here. Just remember, we've got gravity's acting downward, and we'll have to pay attention to our displacement vectors to see which way those are going to work. And we're only worried about gravity right now. We're going to assume that our lifting force, when we do lift, will be a nice even number if we're going to calculate our contribution to work, not gravity's. But I want to do the work due to gravity. For this first segment, the work due to gravity is the same as we had before. It's -200 joules. Let's take a look at this one over here, which is going the opposite direction. We've got our force due to gravity dotted with displacement vector, which is Fg times d times cosine of the angle between them. Now, the nice thing is, in this case, gravity is acting downward. Our displacement's acting downward, so they're aligned. There's a 0-degree angle, so this is a positive one now instead of a -1. So for this component, we've got 200 newtons times 1 meter times positive 1. So we've got positive 200 joules is our work done by gravity. So if we look at this then, I'm going to clear this up a bit. So we've got positive 200 joules when we went down by mistake. We pressed the wrong button on the elevator. Then we went down 2 more meters, and we did double that. That's going to be positive 400 joules. And then we did 1 more meter at 200 joules. You'll notice, regardless if we're accelerating or not doesn't change the force of gravity on the box. What would change is if we're holding this box on our hands, how heavy the box feels to us. So our lifting force changes as we accelerate, but gravity does not. Gravity is pulling us a nice uniform rate, so we don't have any of those issues. On the way back up, once again, force due to gravity is downward. Our displacements are all upward. And so we're going to have negatives again. So we're going to get negative 200 joules. I've got 6 meters up here, so we've got 6 times 2, that's 1,200. Negative 1,200 joules. And we've got up here, we've got negative 200 joules for the last 1 meter. And same math we had before. And if we take and sum all of these, we've got negative 200. I'll do the negatives first. Negative 400. There's negative 1,600, negative 1,800 joules. Plus, in our positive ones, we've got positive 200, positive 400, and positive 200. This is positive 800 joules. So our total is negative 1,000 joules. It matches the last case. So path doesn't matter. So in our last step, we're going to use a pulley, and we'll pull this box up. So you can rope it up to a pulley. You can pull downward, which is the same as if you're pulling upward over on the other side of the rope. So the rope follows our motion. So the rope is actually, our lifting force is still upward, and we've got gravity acting downward at 200 newtons. All right. But really, once again, we're just going to focus on gravity, which is only going to care about these portions here. And gravity is pointing downward in every case. And so here we have our displacement upward. So we still have a negative 200 joule contribution to work there from gravity. We're moving up another meter here against gravity, so it's going to be another negative 200 joules. We're moving up another 2 meters here, which is negative 400 joules. And we're moving up another meter here, which is another negative 200 joules. And if we add all these up, we got the total work done by gravity is negative 1,000 joules. So path doesn't matter for gravity. So in some way, our conclusion is gravity is not the same as us pushing or friction. Somehow friction and you work differently than gravity does. Path didn't matter for gravity. Path did matter whether it was you pushing it or friction working against it.